Okay, this is going to be the second video on center of mass. And if you haven't done it yet, I would definitely watch the first video just to give you an idea of where this information down here came from. And if you watch that first video, you'll be caught up and ready to go on this one. Now, first of all, just a reminder of what the first video was all about. It was about a one-dimensional system. So we had a series of masses, and in a one-dimensional system, they're all aligned on the x-axis. So you only have an x-coordinate to worry about. The steps that we used were pretty straightforward. To find the center of mass of the system, which was this little green dot right here. First of all, we found the total moment about the origin for the entire system. And what the moment was, it's just mass times distance. So it was each mass times its distance from the center, and that gave you the total moment. Then you had to find in step 2 the total mass, and that was just a matter of adding up the masses, each one of the individual masses. And then finally, to find the location of the center of mass, which we called x bar, you would just divide the total moment by the total mass, and that would give you the location of the center. Now, in that problem, it actually turned out to be 2.28, which is where this green thing is. So the idea is if you put your finger right here, you could balance all these masses right on your finger if you put it at that point. So that was a one-dimensional system, and again, a 3-step process. In this video, what we're going to look at is suppose rather than, let's remove the restriction that the masses have to stay on the x-axis, and that's going to give you a 2-dimensional system because each mass now can have both an x and a y coordinate. So first of all, let's take a look and see what that might look like. So we'll actually start with exactly the same masses that we had last time. Let's begin by just moving them around to a different location and change it from a one-dimensional system to a 2-dimensional system. So I'm going to grab each one of these, and suppose I took this 8-kilogram mass, and I'm going to move it to negative 2, 2, and I'll center it at negative 2, 2 right there. Then let's grab the 5-kilogram mass, and let's move it to minus 1, minus 2. We'll put it right here. Then let's get the 3-kilogram mass and move it over 1 and up 3. We'll put it up here. And then finally, let's take the 2-kilogram mass, and this one we'll go ahead and leave on the x-axis, but we'll scoot it over here. So what this is, here's the same 4 masses, but this time they're in a 2-dimensional system because each one has both an x and a y coordinate. Now, as far as solving this thing, in the previous example, and let's go back and take a quick look at that one more time. In a one-dimensional system, you only had 3 steps, and it was a matter of finding the moment, finding the total mass, divide the moment by the mass, and you had the coordinate of the center. And it's almost the same thing here, except that now, rather than just having to worry about an x coordinate, you've got to worry about both an x and a y coordinate, so it actually adds a couple more steps. So I'll scoot this down real quick, and let's take a look at the steps involved first. So in a sense, it's kind of the same thing we had before. First of all, in the first step, you're going to find the moment about the y-axis. Now, in that one-dimensional problem, you just had to worry about a single moment. In this case, you've actually got 2 moments to worry about. You've got a moment about the y-axis, and you've got a moment about the x-axis. Now, you'll still find just one single mass for the whole system. And then the other difference is this. When you find the center of mass, this time it could have both an x and a y coordinate. The x-coordinate will turn out to be the moment about the y-axis divided by the total mass, and the y-coordinate will turn out to be the moment about the x-axis divided by the total mass. So anyway, a 5-step process, and you'll see it's actually pretty easy to use it. So let's run through an example. Now, the first thing I'm going to do is I'm going to write down the coordinates of each one of these things. So the 8-kilogram mass is centered at minus 2, 2. So I'm going to go ahead and put those on here. So this is centered at minus 2 and 2. The 5-kilogram mass is centered at minus 1, minus 2. So this one would be minus 1, minus 2. The 3-kilogram mass, it's over 1 and up 3. So this is going to be centered at 1, 3. And then finally, the 2-kilogram mass, over 2, up nothing. So this is going to be centered at 2 and 0. So what these are going to be, I've got an x and a y coordinate for each point. Okay, now let's start out by first of all finding the moments. Now we want to find the moment about the y-axis, and I think I'm actually going to do this, is when you find it, I'll do this. At first, and it's an easy mistake to make on this, you might think, well, since you're working with the y-axis, surely you would use the y distance, but it's actually just the opposite of what you think it would be, and that's why I went ahead and put this in red right here. So to find the moment about the y-axis, now let's go up here and let's just do this. Let's put a green line right through the y-axis just to highlight it. So I'm going to put that green line. So that's the y-axis. So the moment is the mass times its distance from the axis. So if you notice, what it actually is, it's going to be these horizontal distances here. So it's going to go from here over to here. And what this is going to be, this would be x1. And this distance right here is going to be a -2. Then this distance from here to here, that's going to be a -1. So you're using the x distances. That's going to be a -1. So again, this was x1, this was x2. The distance from here to here, that's going to be x3, and that's going to be a +1. And then finally, you've got the distance from here to here, and that's going to be x4, and that's going to be a 2. So it's interesting that if you want the moment about the y-axis, you actually use the x distances. So with those in mind, let's go ahead and write those down. So let's calculate what that would be. So mass 1 times distance 1. This mass times this distance. So I'm going to have 8 times a -2 plus this mass times this distance. So 5 times a -1 plus this mass times this distance. So that's going to be, the mass is 3, and the distance is 1. And then finally, we've got mass of 2 kilograms times this distance. So 2 times 2. So let's see what that's going to turn out to be. This will be a -16, a -5, a +3, and a +4. And if you add all that together, you'll come up with a -14. Now again, the units, you've got kilograms times mass, so the units are going to be kilogram meters. And what this is going to be, this is the moment about the y-axis. So again, it seems just backwards, but if you want the moment about the y-axis, you use the horizontal or the x distances. So now let's find the moment about the x-axis. So we'll turn those off, and I'm going to do the same thing. Let's look at the distances first. So to find the moment about the x-axis, again, it's going to be a horizontal, so let's go ahead and put that on the axis to start with. I'll go from here, say, over to here. So now that's the x-axis. So the distances are the distance from the mass to the axis. So this time it'll be this distance from here to here. That's going to be, now in this case, it's going to be y1. So the distance from here to here, this is going to be y2. The distance from here down to here is going to be y3. And finally, this one happens to be right on the x-axis, so it's going to be, this is going to actually be y4, but since it doesn't have a length, it'll be 0. So this time, y1 would be a 2. Y2 is a -2. This distance would be 3. And this distance would be 0. So there are the distances. So now with that, let's go ahead and do the calculation down here. So again, when you want the moment about the x-axis, you use the y distances. So it's the vertical distances to the axis. So in this case, it's still going to be the same thing. It's going to be the first mass times its distance, which is 2, plus the second mass, 5 times a -2. So you've got 5, and this distance is a -2. You've got the third distance. Mass is 3, the distance is 3. So this would be the mass of 3 times the distance of 3. And then finally, the last one, you've got a mass of 2, but the distance is 0. So it doesn't contribute anything to the moment at all. So that's going to give you 16 minus 10 plus 9, and then finally plus 0. So if you added all that up, you would get 15 kilogram meters. And what this is going to be the moment about the x-axis. So you've got the moment about the x-axis and the moment about the y-axis. So again, if you want the y moment, use the horizontal distances. If you want the x moment, use the y distances. It seems like it'd be just backwards, but if you look at it, you can tell it's actually the distance from the mass to the axis. So let's go ahead and turn off those green distances. Okay, the next thing you want to do, and we'll just continue through the process here, is to find the total mass of the system. Well, that's just going to be the first mass plus the second mass plus the third mass plus the fourth one. So we'll go ahead and put that down here. So that's going to be equal to, and I'll move it up just a little bit here where I can see it. Okay, so the first mass was 8 kilograms. Second mass was 5. Third mass was 3. And the last one was 2. So if I add all that up, I'm going to get 18 kilograms. And what this is the total mass of the system. So that gives me the total mass. So let's continue on, and we'll find out what the coordinates of the center are. So first of all, to find the x-coordinate of the center, it's the moment about the y-axis divided by the total mass. So again, you use just the opposite of what you would think you'd use at first. So what this is going to be, the moment about the y-axis was minus 14 kilograms per meter, or kilogram meters. So minus 14 kilogram meters divided by the total mass of the system, which is 18 kilograms. And, of course, the kilograms cancel out. And if you divide this, you would come up with minus 0.78. And this is going to be in terms of meters. We'll use that for a distance. And what that's going to be, that's the x-coordinate of the center. Now, to find the y-coordinate of the center, it's the moment about the x-axis divided by the total mass. So the moment about the x-axis was 15 kilogram meters. That's the moment. And again, you use the same mass, 18 kilograms. And again, the mass cancels out. And if you divide this, you would get 0.83 meters. And that's going to be the y-coordinate of the center of mass. So now let's go back up and look at our picture here. And just so we can see it all, let's go ahead and just write these coordinates down. So we know that the coordinates of the center are the following. They are, the x-coordinate is minus 0.78, and the y-coordinate is 0.83. So what this is the center of mass. So let's go ahead and plot that on our picture. So what happens is it's over minus 0.78, which would be about right here, and up 0.83, which would be about right here. So the center of mass is actually, and I think I'll put it in a circle like that. That's going to be the center of mass. So here is what I'm going to call my center of mass. So I've got the coordinates of it, and this is where it's actually located. Now, in most cases, you stop here, but I always get a few students that do this, and they go, what exactly do you have here? The center of mass is not located on any one of those points, so what actually does this thing tell you? And here's something that might make it a little bit easier. Suppose we did this. Let's go ahead and remove the grid. So if we take the grid off this thing, and the thing looks like this. Now picture, you just have these four masses, and suppose they were put them on a glass tabletop, so they're sitting horizontal. If you then did this, if you went up and from the center of each one, so from here to the center point here, and you just got a very stiff wire and connected it. Then you went from the center of this one to this and connected them. Then you went from the center of this one and connected it here. Then you went from the center of this one and connected it here. And suppose this was a stiff rod, and let's assume that it has no mass to it, but at least it's nice and stiff, and you can actually attach these things together. Then the idea is, if you were to take your finger and put it on that point from the bottom, so you're going from the bottom like this, that you could actually balance all four of those things right on your finger. So the center of mass gives you the distance from each one to a point that if you could find some way to connect them, they would actually balance right there. Then if you need to, we'll go ahead and turn the grid back on just to give you an idea, but that's what the center of mass is all about. So again, the steps are, and I think I'll run back through them again, find the total moment about the x-axis, the total moment about the y-axis, find the mass, and then divide them. And the only thing you have to be a little bit careful about is each one is sort of the opposite of what common sense might tell you there would be. If you want the moment about the y-axis, use the x. And down here, the same thing. If you want the y, use the x. If you want the x, use the y. So if you can avoid making that mistake, and again, it helps if you just, we'll turn these green things back on. So if you want the y-axis, use the x distances. And then finally, if you want the x-axis, use the y distances. So fairly easy process. Follow those steps. And what that is, that's how to solve center of mass problems in 2 dimensions using point mass system.